I know it is.
Okay, that's good.
Let me just make sure. Yep, we're good. So, good morning. We're going to get started with the review PowerPoint. This is for my students that are in my classroom right now. We're going to go through each slide that has a learning objective on it. We're going to work out problems and not just me talking, but we're going to go back and forth with questions and practice free response questions and multiple choice questions. So I hope this is helpful to you, but again, this is just me streaming my own personal review. So I hope you understand that I won't be able to answer the questions from the internet right now. But anyway, let's go ahead and get started. There we go. A little delay on my PowerPoint getting open. It'll come in a second. Yeah, it's okay. A little slow. There we go. So, big idea one starts out pretty simple. Ratio of masses in a pure sample. Elements and molecules are made of atoms, and then substances with the same atomic makeup will have the same average masses, and those ratios are independent of the size. So, if we have water, no matter how much water we happen to have, the ratio of the atomic masses, hydrogen to oxygen, will be the same. So that's all that's saying. Here's your first question. A 4.5 gram sample of which of the following would have the greatest mass percent of oxygen. So I'll give you, on these multiple choice questions, about 1.5 minutes because that is how long you'll get on the real exam, and I'll set a timer for these. So do them as my students do them, and then we'll come together. Your time's about half up. If you're struggling to think about what the solution to this one might be, notice they've kind of made this easy for you in that they've given you the molar masses, and then they've given you 4 ionic compounds that all have just 1 oxygen. So if you're looking for the greatest mass percent of oxygen, that mass of that 1 oxygen is going to be 16 grams per mole. So look at the molar masses and make comparisons. You guys in here got it? Alrighty. So if you think about it, since we have 30 grams per mole in lithium oxide, 16 out of 30 is going to be about 50%, and then the other percentages would be lower than that. So that's the first of 100 questions or more. Composition of pure substances and mixtures. Mass percent can be used to determine the composition of a substance. And so if you remember, when you find empirical formulas, the first thing you're going to do is you're going to start with percentages and change that to grams and then go to moles. But it's the empirical formula is that simplest ratio of the moles of each element in a substance. And so I have this little poem that I tell my students, and it's right here: percent to mass, mass to mole, divide by small, multiply to whole. And so the molecular formula you can actually figure out by dividing the mass of the molecular mass by the mass of the empirical formula. So let's look at that. So a compound is determined to have 14 grams of nitrogen, 32 grams of oxygen. The empirical formula is which of these? So again, percent to mass, mass to mole, divide by small, multiply to whole. In this situation, they already gave you mass, so you don't have to take percent to mass. It's already given to you. So go ahead and get that one started. remember, you don't get a calculator on the AP exam for multiple choice. So if you're using a calculator at this point, you don't need to do that. They'll give you masses that are easily converted to moles. So as you're looking at this, you should be thinking, okay, well, the molar mass of nitrogen is 14, and the molar mass of oxygen is 16. So it should be a pretty quick one. My guys in here are still working, so I'll give y'all another minute. You may not need the whole minute and a half on this one. Okay, so just in your head here, or on paper, 14 grams, like I said, of nitrogen is 1 mole, and 32 grams of oxygen would be 2 moles, so pretty quick. If you look, hopefully you got the answer to be C. So if you're ever given grams on the AP Chemistry exam, there are very few situations where grams is actually useful to you. If you don't know what to do, when in doubt, mole it out. And in this case, if you went to moles, you would have seen that there was 1 mole of nitrogen and 2 of oxygen. So there you go. A purity of a substance, a lot of times they will give you a sample and maybe they'll ask you, well, if this happens in the lab, then what does that do exactly with your data? So impurities in a substance can change that percent composition by mass. And so if more of a certain element is added from an impurity, then the percent mass of that element will increase. So a minute ago, when we talked about lithium oxide, if we had some more oxygen from some kind of contamination, then that would increase the percent mass of oxygen above 56% or whatever we found. When heating a hydrate, the substance is heated several times. You've probably done a hydrate lab in your chemistry class. This is copper 2 sulfate that you're seeing right here. And so, it will turn sort of a white color when all the water is driven off. And so notice what you're going to do for good lab practice. You would heat it and mass it and heat it and then mass it and heat it and mass it. And then once the mass starts to stay the same, you quit. And that happens a lot of times when you're filtering things out with gravimetric analysis, which is just using gravity to filter something out, and you'll mass it and dry it again. So here is another question. I'll go ahead and get the timer started. Mass percent of oxygen in a pure substance glucose is 53.3%. A chemist analyzes a sample of glucose that contains impurities and determines the mass percent is 49.7%. Which of the following impurities would account for the low mass percent of oxygen in the sample? This is actually really close to a real AP exam. We changed it up a little bit, but very similar. You guys got it? Okay, so the mass percent of oxygen is lower than it should be. So if I'm looking at all my choices, the elements in here are carbon, hydrogen, oxygen. So if I pick A, which I see that most of my guys did, that doesn't have any oxygen in it. So if you add that in as a contaminant or an impurity, it's going to lower the percent of oxygen. So it has no oxygen, so I guess it has the lowest percent by mass. Mole calculations, like I said already, when in doubt, mole it out. If you see something in grams or atoms, probably going to need to go to a mole. And so the way you do that here, you can see that grams, you're going to use the molar mass. And then anytime you have particles or molecules, you're going to use Avogadro's number. You should never use Avogadro's number with grams because that weighs more than the moon. So be careful there. So how many moles of carbon are in 88 grams of propane? Oops, I forgot to stop that last one. Excuse my computer. There we go. There we go. All right, now I have a cursor, so that's good. See a couple people still working. You have about 30 seconds if you're still working. So time's up. So here in this situation, we have grams. We're going to go to moles of propane, and then we're going to need to go to moles of carbon. So if we do that, I'm actually going to work it out a little bit more for you in case you need it. You should have gotten C. So, oops. So if I have 88 grams of C3H8, we're going to need to go to moles. So 1 mole of propane. What's a molar mass of that? 40. Which one? 44 grams. And, you know, this is, again, multiple choice. So you kind of can already see that that's going to be, you know, 2 moles right there. And then in each mole, and 1 mole of C3H8, we're going to have 3 moles of carbon. And that's coming from right here. So if I just kind of work this out in my head a little bit, you know, we're going to get that it is 6 moles because we already said that this was like 2 times 3 is 6. So far so good? Okay. All right. Electron configurations. So those first couple slides were real chill, just kind of like first year chemistry stuff. And so is this, but we're going to start getting into electrons and PES here and orbitals. So electrons occupy orbitals, and that depends on the average distance to the nucleus and the energy level and all that. So electron configurations and orbital diagrams are going to start or indicate, the lowest energy. So electrons are going to occupy the lowest available energy levels, and then if you recall, each orbital can only hold 2 electrons, and they have to have opposite spins. In orbitals of equal energy, electrons are going to maximize parallel unpaired spins. What this basically means in like plain language is that electrons are going to occupy orbitals one at a time until they have to share, which is Hund's rule if you're thinking about that. If you're taking the AP exam and you're asked to explain something, you cannot just say because of Hund's rule, or if we were talking about equilibrium, because of Le Chatelier. Just leave names out and talk content. So knowing the person's name won't get you any credit. You need to actually describe the phenomenon. So which of the following electron configurations in orbital diagrams represents silicon, element 14? So if it's element 14, then right off the bat, you know what that means as far as the number of electrons. Oops, I didn't mean to do that. I'm sorry. My bad. It'll come back, no worries. I'm just trying to get my pen to where I can write on the board. I feel like that's important today. There we go. Did you guys have enough time already when you saw it before? Yeah? Okay, so if I look here, I can already tell, like on A, that these two electrons are paired. I don't even know if this is the right number of electrons, but I can tell right off the bat that that's not okay. So I can throw that one out just before I even start. Also, this one here is missing 3p, so that's kind of necessary. So the answer is either B or C, and so I need 14 electrons. So, and this one, they have 3s1. So this could actually happen when an element is excited, when the atom is excited. Electrons will go up to other energy levels. So when they come back down, that's when they emit photons, and we see different colors of light. So this is possible, but this is in an excited state. So did you guys get C? All right, cool. So ionization energy. Ionization energy indicates the strength of Coulomb contraction of the outermost easiest to remove electrons. In simpler terms, it is the energy needed to remove an electron. Okay? It increases across a period and down a group. It increases in the same energy level as you increase the number of protons because you have an increased effective nuclear charge. So ionization energy decreases as electrons are in higher energy level. They're farther away from the nucleus, so that means there's a decreased Coulomb contraction, because if you remember Coulomb's law is charges multiplied divided by the distance. So the distance being further is going to decrease the Coulomb contraction. So which of the following groups of elements is arranged correctly in order of increasing first ionization energy? Be careful when you're reading questions like this. You want to make sure that, if it says decreasing or increasing, you may want to, even on your paper, write yourself a little note, like I'm looking for lowest to highest. You don't think you'd mess that up, but when you're under a lot of stress, you might. So I think taking 2 seconds to make a little note as you work it out would probably help. So ask yourself, which one has the lowest first ionization energy, and then which one would have the highest? You guys got it? Okay. So when we're looking at this, remember that the larger the atomic nucleus, the lower the ionization energy, because the Coulomb contraction will be decreased because the increased distance between the nucleus and the energy level, the outermost energy level. So for sure, I think I can safely say that it's either A or C, right? And then once we start looking at nitrogen and carbon and fluorine, because as you are adding more protons within that same energy level, they're all in period 2, that's going to increase the ionization energy across that period. So if we look at those, that pattern, you can see the answer is A, because if you read across the second period, it goes carbon first, then nitrogen, and then the question didn't talk about oxygen, but then fluorine, and that's fine. So there's, since the valence electrons are in a higher energy level that is better shielded, the first ionization energy must be lower than that of carbon, and that's just talking about magnesium there. So just one more time, I know you get tired of Coulomb contraction, which is, I'm sorry, because we're going to say it a lot today. The increasing nuclear charge, which is the number of protons is increasing from carbon, nitrogen, and fluorine. So that's going to increase the Coulomb contraction to the nucleus. Because they're all in the same energy level, we can kind of take out that whole distance piece of it. So electronic structure, PES. PES uses high energy photons to excite electrons, and the electrons can get ejected, and so you can actually figure out the energy of the photon if you subtract the kinetic energy. Don't worry about that super a lot, but what this is showing us, you need to be able to read these graphs here. And if you recall, some of them, just be careful, read the graph. Some of them will show the ionization energy decreasing across the x-axis, and some will, I've seen some that show increasing. So make sure you read the data. But notice here with this 1s2, that has a higher ionization energy, if I'm looking at lithium, than the 2s1 electron, because this electron is farther away from the nucleus, so there's decreased Coulombic attraction. And then the relative height of this graph, like this one is twice as tall as this one, so this shows that 2 electrons are ejected when I apply this much energy, but only 1 is ejected. So that's my 2s1, or excuse me, my 1s2 orbital, and then that's my 2s1. There's only 1 in there. So there is a break, like with neon here, that shows that there's a big difference between the ionization energy, or the energy needed to remove the inner electrons on neon, and then these require much less energy because they're farther away from the nucleus. So, which element would be represented by the complete PES spectrum above? So I like how they went ahead and marked on here relative number of electrons. That could probably be helpful to you. Notice this one reads from large to small. The way they've done the y-axis is a little tricky. Did y'all notice that? Yeah. So you got to think about the data. You know how many electrons should be in each orbital. So, you know, in that first, this first piece of data here, if you don't think about it, that looks like there's 4, right? But there's the 4. No. You guys got it? Okay. So if I look at this, this is the most energy is going to always be that first little spike on the PES graph will be your 1s2. With the one, wherever it is, if it's, you know, highest energy over here, then that's fine, but it is highest energy is here. So my 1s2 electrons are here. So that really shows me that 2 of these units is 1 electron. So that's my 1s2, that's my 2s2, and then I have 2p, 1, 2, 3. So if I look at that, that is C, so nitrogen ends in 2p3, right? Okay. Electronic structure, higher ionization energy, so second and subsequent ionization energies increase as you remove electrons. So no matter, you know, if we're talking about sodium or we're talking about neon, it doesn't matter. The first ionization energy will always be less than the second ionization energy. It doesn't matter if where it is placed on that periodic table. There is a large jump, and they like to ask questions about this. There's a large jump in ionization energy when you start to remove less shielded core electrons. So you'll see, let me show you right here. For example, in beryllium is in the second period, and it has 2 valence electrons. So if I remove the first valence electron, there's first ionization energy, and then the second ionization energy will always be greater. But these are my valence electrons. Once I remove them, I have decreased the distance. These are all the inner core electrons, and so they're much closer to the nucleus, and so they'll have a higher Coulombic attraction with the nucleus. And so you see a big jump right here. And so what they might do is they may have all this covered up, and they might say, this is element 4. And so they might say, what element might element 4 be? And you have to go, well, if it's in the second period, they'll give you the period. Okay? And then you would have to say, okay, well, there's a jump, which there's always a jump at between ionization energies. It's always going to go up. But when there's a big jump, like a marked difference, then I would say, okay, well, there's 2 valence electrons, so that would tell me that's beryllium. Okay? So the ionization energies for element X are listed above on the basis of data. Element X is most likely to be which one? You guys got it? Okay, cool. So if I'm looking here, I can see there's a big jump between the 4th and the 5th ionization energies. So that tells me there's 4 valence electrons. So when I start looking at the periodic table, the only one listed that has 4 valence electrons is carbon. So basically, if it helps you to think about it, the big jump happens after the number of valence electrons you have. So it happened after 4, so I have 4 valence electrons. As you start looking at this a little bit more closely, the first ionization energy is going to decrease from beryllium to boron. So you can see there's a little bit of a dip there. There's an overall increase across a period, but there's some anomalies here. So let's talk about that. Why does that happen? An electron in the 2p or 3p is shielded by the 2s or 3s electrons. So you can see that the first ionization energy increases from lithium to beryllium, but it goes down when I get to boron because boron's 2p1 electron is going to be farther from the nucleus. The 2p energy level is higher in energy than the 2s. And so there's going to be less energy needed to remove it. And then there's another little anomaly here when I go from phosphorus to sulfur or, for example, nitrogen to oxygen. So what's happening there, I'm going to try to draw this out. I think that will help. Get a little pen here. So if this is my 2s orbital and then my 2p orbitals, let's just talk about the second energy level real quick. So this is lithium and then beryllium and then boron. So this one's going to be easier to remove. The ionization energy will be less because there is more energy, and this is a farther distance from the nucleus. Now, these are going to continue to fill one at a time as I go to carbon and then nitrogen. But check it out. This little dip from nitrogen to oxygen, the reason why that happens is because this electron, this 2p4 electron for oxygen, it's now in a shared orbital. And so there's going to be repulsion from this electron that was already in that orbital. And so you have this temporary little dip in the data because of the repulsion in this orbital with the one that was already there. Yes, ma'am?
So when you complete a sublevel like 2s, beryllium, that's like not exactly like it's gonna be a stronger ionization energy. Like if it completes a sublevel.
Yeah. So it's going to take more energy to remove this electron than it would this one. If we only had 3 in the second energy level. Yeah. Gotcha. So anyway, that's why this is happening. And this same thing happens in the 3rd energy level and the 4th energy level, and that's why. So I need to erase my little. I don't. Anybody got an idea how to erase this? No, I'll just leave it. It's fine. So it's totally fine. I think if I go on, don't look. That's the right way. Okay. Given the PES spectra for phosphorus, sulfur, and which of the following best explains why the 2p peak for S is further to the left than the 2p peak for P, but the 3p peak for S is further to the right than the 3p peak for P. Wow. I feel like that was a tongue twister. It's a little too early for this mess. I'm going to give y'all a second to look at it, and then I will kind of come back behind you and start to help you out with it a little bit. Oh, oops. This is, in my defense, this is not how I normally run my PowerPoint, so we'll just wait. Did y'all have enough time to look at it? Yeah. Okay, so if we go ahead and show that answer that I've shown you twice. The answer is A. So, sulfur has 1 more proton than phosphorus, so it's going to have a higher effective nuclear charge. However, because it has a 3p4 configuration, you're going to find that whole little electron repulsion phenomenon that I just talked about happens. And so that's going to reduce that Coulombic attraction, and so it's going to have that lower binding energy or ionization energy. So y'all pretty good with that? They really do like to ask about this little phenomenon with a dip there. Pretty straightforward though. So periodic trends, electrons are attracted to the protons in the nucleus. If that makes sense. Now that we've said it 6 times, here's Coulomb's law, right there. The more protons that are in the nucleus, you're going to have a higher effective nuclear force. And so it's going to attract the electrons more strongly. Electrons are repelled by other electrons, and so if valence electrons are shielded from the nucleus by other electrons, you're going to have less attraction there. A summary of the trends, as you go down a group, you're going to be adding energy level, so the radius increases. And then basically, I explain this in great depth, so I don't want to dumb it down for you. But you go down, the atom gets bigger, and then you go across, it gets smaller. And then ionization and electronegativity have opposite trends as size. There are reasons for that, and they all go back to Coulombic attraction, but if you need to think about it real quick, that's a good way. So given the atomic radius and the first ionization energy of sodium in the chart below, which pair of values would most likely be the values for magnesium? So find sodium, magnesium on the periodic table. You'll have a periodic table on the AP exam. It'll be in the front of your booklet. You can't tear it out, so you can certainly flip back and forth. But I know you have one in front of you now, so just heads up on that. I think my kids are done. Y'all done? So as I go across a period, I would expect the first ionization energy to get larger and then the radius to get smaller. So the only one that has a larger first ionization energy and then a small radius is A. And so that's what we found the answer to be. All right, so trends. If we look at some just basic stuff here, we have, nonmetals make molecular compounds. Ionic solids happen when you have big electronegativity differences larger than like 1.9 if you look at electronegativity values. The first element in a group is going to have, if we go like down a group, for example, if we go down a group like the alkali metals, it is going to have stronger bonds in molecules and single bonds. All this is pretty straightforward stuff. So as far as something a little bit more applicable here, of the elements below, blank reacts most quickly with water. So when you're answering this question, think about the electrons that are going to be involved in the reaction, and then think about Coulombic attraction of those electrons with the nucleus. You guys got it? Yeah. So this one's going to be cesium. You may have picked sodium because, you know that sodium reacts violently with water. But cesium is in the same group as sodium. And so its valence electron is going to have a much lower Coulombic attraction with the nucleus. So it's going to be able to be transferred a lot easier. So don't just go with what you think. Go ahead and look at the actual periodic table. So chemical properties within a group and across a period. Group 1 metals are more reactive than group 2 metals. That's because the ionization energy from group 1 to 2 increases. So there's going to be more energy needed to remove that electron, or those 2 electrons. So that's the little details there. That's helpful, but let's go ahead and look at this. Which of the following groups from the periodic table would be easiest to oxidize? Now, you got to remember that oxidation, this is where that Ulrich thing comes in. Oxidation is losing an electron, oil, and then reduction is gaining, Rig. Okay? So which one of these is going to be easiest to lose electrons? Oxidation is lost. You guys got it? All right. So the answer is D. Oxidation involves losing electrons, so the group of elements that has the lowest ionization energy would be the easiest to oxidize. So if we wanted to order the rest of these, we would see that, alkali metals would be the easiest, then probably alkali earth metals, and then of all of them, it would be very difficult to oxidize halogens. And you can't say, well, halogens just want one more electron to be like noble gases. You can't pull that. That's like first year chemistry. Be careful because atoms don't have personalities, and they don't personalize them. Don't give them human traits. It's very common for people to do that. Don't do that. So the thing is, halogens. The answer would be halogens have the highest ionization energy if you're looking within a single period, and so it would take the most energy to remove electrons, which is oxidation. So that's the answer. Not they're almost like a noble gas, and so they want to keep their electrons. Don't say that. So if we look at the Bohr model, we know orbitals are where they probably are within a 90% probability. There's some evidence for this, and like I said, Bohr's model has these energy levels, and there's some other work here. Quantum mechanics kind of takes that a little bit farther with the orbitals. I should have said that Bohr has these fixed energy levels, and then later on with quantum mechanics we added the orbital idea. Heisenberg uncertainty, we don't really know exactly where the electrons are, because if you go to measure them, you would interfere with them. And so here's that same data for ionization energy, and just to make sure you got it a minute ago, this dip in energy is as I go from the S sublevel to the P sublevel, and this is as I go from P3 to P4. Okay, and so as atomic number increases, we would expect ionization energy to constantly increase. So the graph doesn't show that, and so this data is actually provides evidence that electrons are not just in fixed energy levels; they're actually in orbitals of different energies within an energy level, those sublevels. So this actually provides evidence that Bohr's model was incomplete, and we need a little bit more data. All right, so the data below shows the first 10 ionization energies in kilojoules per mole for an element that is found in period 3 of the periodic table. So identify the element, and then there's two questions. Which ionization energy corresponds to electrons that would account for the peak in photoelectron spectrum of the element that has the lowest energy values? I wish you well. Answer one at a time. And I kind of mentioned this a minute ago. They did throw that in what period you're in. That'll be there most of the time, so you need to kind of hunt for that, because the data trends in any period would look the same. The values would be a little different, of course. Have y'all correctly identified the element? Yep, you found the big jump, right? So that would mean it's magnesium, because you have a big jump. Look, this doubles, but this goes up, by a factor of like 5 or 6. So that's your big jump. Go ahead and do the second one. This one's worded kind of tricky. You got it? Do you understand what they're asking? All right, let me kind of break it down for you. Which ionization energy? So you got 10, so pick 2, okay? Because they're giving you, well, no, pick as many as needed. Which ionization energies correspond to electrons that would account for the peak in the PES spectrum of the element that has the lowest energy values? So you got to think, when I have a PES spectrum, I want my little pen to show up, but it won't. When I have a PS spectrum, I have a peak for each orbital. So the lowest energy on that PS spectrum is going to be the outermost orbital, the highest energy orbital. So y'all figured out that this is magnesium, right? And so if I'm looking here and I have to think about it, this is my 3s2 electrons. This is my 3p6. Is it 3? Yeah. 1, 2, 3, 4, 5, 6. And this is going to be my. I'm going backwards. This in my head. Excuse me. Let me think about that again. Well, no, I'm saying 2. I said 3 instead of 2. Excuse me. So let me start over. I need to make another chart, but it won't let me write on top of the questions. I don't know why. The 9th and 10th ionization energy are going to be your 1s2. So you kind of can look at it backwards. Like these would be the 9th and 10th electrons removed. They didn't give you all of them. I would need 11 and 12. Look, magnesium has 12 electrons, right? So if I had 11 and 12, that would be my 1s2 electrons that are not shown here. Okay? And then these two would be my 2s, right? And then you can follow the pattern. So it would really be the first and the second ones would be the last ones. It's backwards, right? Because PS is showing the orbitals, and this is showing the ionization energies. And if they had given you 12, it would have been a little bit easier to figure out. So it is the first and the second one. Do I need to go and draw that on another paper, or do y'all get it? Yeah. That was a little tricky. I almost messed up there because I was thinking, okay, well, these are the last ones, but that wasn't right because there's 12. All right, mass spectroscopy. They will ask questions about this, and so if you remember, the mass spectrum of something shows you the relative abundances of the different isotopes. And so when we look at the periodic table and we see the atomic masses, they're not round numbers because you have to find the atomic mass through the weighted average of the isotopes. And you get the numbers, the data for the percentages by looking at these graphs. So if I'm looking at bromine, you can see I have a couple peaks here at 80. If you recall, bromine is diatomic. And so these would be just single, these would be data picked up from just bromine atoms, and this would be your Br2. And so if I look, the most abundant isotope probably weighs 80 because I have a big peak at 160, right? And then I have some that weigh a little more and a little bit less. This is probably 162, and that's probably 158 because it is the atomic, you're going to have part of a number. And so if you recall, the way you do this, you find the average mass the same way you find your grade in the class. You take the mass of it, and then you multiply it by the percent weight or percent abundance, and then you add them up. So here is a good example of that. And you can see we have similar atomic masses, and this is the mass sample that is believed to contain both. Which of the following statements would be the best explanation for deciding that a sample contained only zirconium? Do you have a question? Can I help y'all? Oh, okay. No, I don't mind. Anything y'all need, just let me know. Well, as I look at these answers, does it matter for mass what the electrons are doing or how they're paired? So, or if it has a charge, right? So if I look at this, you could think about it a lot. You could actually do the math and find the average atomic mass. But that mass is not going to be affected by if it's an ion or not. Electrons have little to no mass. So really just G then. Right. So I was like, you could really look at the data and analyze it, and you may be asked to, if I go back, you may be asked to do this. Like, if you had to find the atomic mass of this, it would be 90 times, about 50%, so 0.5, and then 91 times 0.1, and then 92 times 0.18, and 94 times 0.18, and 96 times, 0.2, or whatever it is. And you would add those up, and that would give you your mass. This question is not asking you to do that. Okay, so there are 3 different types of spectroscopy, other types of spectroscopy. And so in this situation, we're talking about infrared and UV or X-ray radiation. This is kind of one of those situations on the AP exam that they are testing, but the kinds of questions they're asking are pretty basic, and it's kind of one of those shady places. This is how I think about it. Infrared radiation. Infrared radiation is what we feel as heat, which y'all know from AP Environmental, but that is going to cause the molecules to vibrate. So vibration is infrared. Ultraviolet or X-ray radiation, what's going to end up happening there, those electrons, you're going to have transitions. And so you're going to have electrons getting excited, going up energy levels, and coming back down. That makes sense, right? This high energy coming into them. Microwave radiation, I remember that caused rotation because a plate in a microwave rotates. I'm done. Like that's the extent of what they've asked on this. So that should get you, if you are asked questions. There was number 50 on, I think, the test 2 years ago. It just had matching them up, and we had looked at that a couple times. Oh, here you go. I actually put this in there as a throwback to number 50 a couple years ago. Which one of the following contains a transition paired with correctly with an area of high absorption in the electromagnetic spectrum? So think about the 3 things I just told you and which one's paired up right. You guys got it? Pretty quick, right? So transition would be the UV or X-ray, so that one's not right. So again, no. Rotation and infrared, no. Vibration and infrared is the correct pairing. So D, yay. Beer's law, all right. When you're using Beer's law, what you're going to do is you can apply this to kinetics, for example, and look at how fast the color fades. If you recall, we're going to take a solution and we're going to it has to be colored, so make sure you pay attention to that. This wouldn't work with a solution of something like sodium chloride because it doesn't have a color. So this only works with colored solutions. You're going to use a colorimeter or a spectrophotometer. We use colorimeters, so that's fine. And then this formula is actually on the formula sheet. If you look, so A equals ABC. I think this is just, I thank them for making this easy to remember. But if you recall, you're going to use and choose a wavelength of light that is sort of the complementary color on the color wheel. So I kind of, to me, I haven't seen a lot of questions to that effect. Like if you have a green solution, you want to use, red wavelengths of light in the colorimeter. We talked about that. I don't think they have gone into that a lot, but if they do, well, there you go. So A is the absorbance, and then the little a, the molar absorptivity, it changes. It's a constant for different substances. A lot of times, you'll use the graph to find absorbance, and then you'll have the path length in the question, usually it's 1 centimeter, and then the concentration, like the molarity, will be given to you. And what you'll have to do is you'll have to fill that in, solve for A, and then in part B of the question, they will ask you to apply, this constant to solve for an absorbance at a different concentration or something. So that happens a lot. So if you're asked questions on this, generally the way it goes is you're going to have to solve for this A value and then use the formula again to apply it. So heads up on that. So here is an example of some data that you might have to look at. Using absorbance versus concentration, and that's typically the way the graphs look. A student is trying to determine the concentration of an unknown substance, and if they measure the absorbance to be 0.4, what would be the concentration? This should take you like 5 seconds. Questions like this count just as much as questions that take you 10 minutes, so these are the ones you want to go ahead and answer. So 0.4 intersects on the graph around, right here, around 0.56, right? So no problem there. Did I answer this wrong?
Yeah.
What? I am the saddest person on earth right now. So I'm gonna have to take AP. I'm gonna have to take chemistry in college because I'm gonna fail the AP exam. It's totally fine. So the absorbance on my own papers, when I'm answering questions, and I've taught y'all this before, I will like circle what I'm solving for, then I don't screw up. But anyway, let me start over. The absorbance is 0.4, right? And so the concentration, if I follow it over, is going to be B, 0.28. So I'm sorry. It's like, this is so easy. When we get into the lab part of it, there's like a lab component at the end of the PowerPoint. We'll talk about, if you recall with these, you have to make sure you don't have any smudges on it because the smudges will actually absorb some of the light that's going through your little cuvette, your little glass thing with a lid on it. And so that will increase the apparent concentration of the solution. So sometimes they'll have the data and it'll have like a, have a smudge or something. So you'll have a temporary kind of outlier for concentration being a little higher than it should be. Yay, particulate models. Woo! Law of conservation of mass. You wish that they ask you, well, if the reactants weigh this much, the products weigh the same. But what it's really going to be is you have to sit here and go, okay, I started with 1, 2, 3, 4, 5, 6 times 2, so 12 hydrogens, and then over here I should end up with 12 hydrogens. I start with 4 nitrogens, I should end with 4 nitrogens. And so this is a particulate model of the law of conservation of mass or matter. Good times. Yay, particulate models. The picture above is a representation of hydrogen and oxygen in a sealed container. Which of the following pictures would be the best representation of the products if the reactants were to run to completion? So before you even look at these answers, the number of circles and the type of circles has to match what you started with. These seem really easy, but they're easy to screw up too. Yes.
I don't know if this matters, but the virtual audience cannot see the questions.
They can't see the questions. They only can see the...
I guess.
Well, they should have came.
Well, I can't do anything about that. Should I just turn it off? I don't know. They can't. I don't know. It's sharing my screen, so I don't understand why they wouldn't be able to see the questions. I'm sorry if you can't see the questions, but if you think about it, and you could follow along, you could actually follow along in the PowerPoint and listen to the audio on your phone or something. There you go, smart children of the world. I do apologize. Anyway, so if I look at this, I think I figured out how to make the pen work, so I'm excited about that with the questions, so maybe we'll figure it out. If I look at the balance equation, which is always something good to start with, for every 2 hydrogens, right, so for these 2 hydrogens, 1, 2, I'm only going to need 1 oxygen, right? So I should come out of here with 2 waters and 2 oxygens left over. So, and the oxygen's diatomic, right? So this is not okay. So, right, did you get that? After missing that absorbance one, I'm like, do I know what I'm doing? Doubt my life a little bit. So if we look, the answer is D. If you look at the bounce equation, you can see the ratios there. Alright, so use mole ratios and bounce equations to calculate moles of unknown substances. Mole ratios, if you recall, are just conversion factors or fractions that show you the coefficients in the bounce equation in a ratio. So use the bounce equation below, the combustion of propane, calculate the number of moles of CO2 produced if 3.52 grams of propane are burned in excess oxygen. So anyway, if I want to, if they don't give it to you balanced, which they usually do, you need to balance it. But then whenever I'm solving for this, these are kind of my choices for coefficients 1, 5, 3, or 4. And so you can see here as they solve, here's your mole ratio that's needed to go from carbon dioxide to propane. So no big problems there. So gravimetric analysis, what you probably did in your class, you probably didn't use lead, and what we did, we made silver chloride, and what we did was we started with silver nitrate, and we added, it might have been sodium chloride, something with chloride in it, it doesn't really matter as long as the cation doesn't react, but we ended up making silver chloride instead of lead chloride. But what you would do is you can use suction or you can just use gravity. Our solid, our precipitate, was kind of trapped and then the water was kind of sucked through. So that was fun. And we can determine the mass of what we collect. And remember, you want to, dry that and mass it repeatedly to make sure that all the water in your precipitate is gone, and you're just at that point just massing your silver chloride or your lead chloride. All right, so here is this is actually a FRQ. So this is going to take 20 minutes, right? So you can use your whiteboard, or you can use, yeah, everybody's like, no. But this is a real FRQ. So give yourself about 20 minutes to work on this. We're going to work on it and talk about it, and then we'll take a little break after we do it. So I'm going to set a timer. I'll give you about 20 minutes. I'll give you 22 minutes. Bless you. On your mark, get set, go.
see what you mean. You had 8 earlier.
But you could just follow along and then listen to the audio if you really want to do it. And the people that are out that are in US history, like,
They're gonna want to do it.
you could just have your computer and play the file. Share the file. I can give you the file. Yeah, I have the link for the PowerPoint.
Should be. Yeah, you have to if you want to sign it.
Yeah, I do.
The Untitled.
Oh, it's so long.
No, I think I read it.
You think you read it wrong?
Is this just not PBI too? Or is there more to it?
What's the number?
Okay. When it's asking for the math percent, isn't that really easy? Or no? Easy.
You would just take the.
There's an inert water solution. What's that?
I don't even get any more from here. So,
Can you just go on?
No, sir.
yeah, I don't get any more from here. I have 0 bars of services.
Ross, I'm gonna send you this.
I have rooms.
You can comment on the video and press the link to the web.
So I gave you 22 minutes, and only about 10 minutes have gone by. So if you're freaking out, you still have time. You're okay.
I'm freaking out when you started talking. I was like,
Wait,
what?
is that how much time we have?
So this is a long FRQ, and you can tell because it's a number 1. So yeah, you're
And the snack.
So we get that much time technically?
well. They actually, lengthen the FRQ time. So this is the only exam that goes over 3 hours. The FRQ time I think is 105 minutes. It used to be 90. So then you have the 3 long and the 4 short. So if you do the math, I think they say give 9 minutes apiece on the short ones and low 20s on the long ones. I can look back at the numbers. But you still have time, so no worries.
Not a lot of posts. Not a lot of putting the links. No, why don't you just put them in the description?
Why aren't you allowed to?
I don't know. That's what. You just put in the description of the video.
That's really odd. I guess it only plays the bottom side of the PowerPoint and it doesn't show the stuff that pops up over the top. I would have never guessed that was going to be an issue.
Usually I was like 10 slides back.
Yeah, there is a time delay for sure.
Do you see the slide that we're on?
No.
No, you don't. It's on the Electron Configurations.
Yeah, I'm going to add in the link to the I want to add in the link, but I don't have it. I have it on my phone. I don't have a good answer for that.
Okay, now it's working.
Good question. They should be able to see. I don't think.
Oh, that's good. Because it's kind of like a 5-second delay. when you go to full screen, it's
Well, if I don't go to full screen, you can't see the light. You understand?
yeah.
So that's the issue.
I don't have, the way we designed it for like one side, I think.
I don't know that.
Yeah.
I think we're on YouTube is kind of the issue. I don't know if that's a sufficient.
I got an idea. All right. As far as time goes, you have about 5 more minutes. Can't see anything I write.
Even on the PowerPoint?
Yeah,
It's pretty hard to know.
yeah. I think I'm tapping out.
Because I'm pretty sure they can read the questions themselves.
Yeah. And whatever I point to, you can't see. You can't see anything. Oh well. I tried to get credit for trying.